Hello everyone. In this video, we'll be discussing my solutions to the AP Physics C Mechanics 2022 released exam FRQ questions. And this is for the Set 1 released questions for the 2022 exam. As a disclaimer, I do not own any of the questions below. They are the sole property of the College Board, which does not endorse this product. I will be discussing my own solutions to this exam. However, I will be pointing out the grading criteria used by the College Board when assessing students' answers. These grading criteria can be found on the released exam. Let's begin. To start, consider the following setup. A block of mass M is pulled across a rough horizontal table by a string connected to a motor that is attached to the floor. The string passes over a pulley with a negligible friction that is vertically aligned with the left edge of the table as shown. The string and pulley both have negligible mass. The pulley is at height h above the table. The motor exerts a constant force of tension Ft on the string, and the block remains in contact with the table at all times as the block slides across the table from x equal L to x equals 0. The coefficient of kinetic friction between the table and the block is mu sub k. Express all algebraic answers in terms of m, h, ft, x, mu k, L, and physical constants as appropriate. Moving on to question A. On the dot below that represents the block, draw and label the forces, not components, that act on the block when the block is at x equals L. Each force must be represented by a distinct arrow starting on and pointing away from the dot. Well, looking at the system in question, we have the gravitational force, which points downward. And this gravitational force is given by F sub g. Of course, we know that this is equal to mg. Next, to counteract that force, we have the normal force. Since we have tension in this problem, I won't give an exact form for the normal force. I will leave it as F sub n. Next, we have the tension force. This is pulling diagonally at an angle of theta. And we'll label this force F sub t, the tension force. Finally, we have the friction force. Since the block is moving to the left, the friction force wishes to oppose this force and this movement, and so the friction force points to the right. And I will label that F sub Fr, with a force of friction. And this is given by mu k times the normal force. So these are all of the forces acting on the block. As a note, students get 1 point for having both F sub g and Fn labeled correctly and pointing in the right directions, as seen here. Students get another point for having the force of friction, the one pointing to the right here, labeled correctly and pointing in the right direction. Finally, students have 1 point allotted to them for having the tension force, which points diagonally upward here, correct. Any extra vectors or forces on this diagram allows a student to earn at most 2 points. So students lose at least 1 point if they have any additional vectors other than those labeled here. Next, derive an expression for the angle that the string makes with the horizontal as a function of x. Well, we know that our system forms the following triangle. We have a string which goes up and then over a pulley and goes diagonally downward to the block. At this block, we have an angle of theta, and we complete the triangle by using the dashed line, which is supposed to be the surface of the table. The left side of this triangle is x equals 0. and the right side near the angle is x for some value of x, wherever the mass is. We know that the height from the table to the pulley is h. Moreover, we see that the side length here is x. So we can use trigonometry to solve this problem. There are three solutions to this problem, which we can use SOHCAHTOA for. Firstly, we must note that because we know two of the side lengths of this triangle, we know that the hypotenuse should be x squared plus h squared. Then we note that if we wish to use sine as the trigonometric function in question, we would have sine theta is equal to the opposite side length, h, over the hypotenuse, which here is square root x squared plus h squared. Alternatively, we could use that the cosine of theta is equal to the adjacent side length, which is x over the hypotenuse, which is x squared plus h squared, all to square root. Finally, we could use the tangent of theta, and this is equal to the opposite side length, h, divided by the adjacent side length, which is x. For each of these, we use the inverse of the trigonometric functions, so arc sine, arc cosine, and arc tangent, to get theta as a function of x. So, for each of these individually, we find that for sine, the answer is theta of x, so theta is a function of x, is equal to arc sine, or sine inverse, of h divided by square root x squared plus h squared. Alternatively, we could, for cosine, see that theta of x is equal to arc cosine, or cosine inverse, of x divided by square root x squared plus h squared. Finally, for tangent, we can use arc tangent, or tangent inverse, to get that theta of x is equal to arc tangent of h divided by x. So, any one of these solutions on the right is perfectly valid as an answer. You only have to put one in order to get full marks for this point, for this part of the problem. You get 1 point for using a trigonometric expression relating theta to x. So you get 1 point for putting any one of these expressions on the left. And you get 1 point for having the correct trigonometric expression given on the right. So you get 1 point for this on the left and 1 point for the boxed solutions on the right. Again, you only have to put one of these for full marks. Next, in C1, we wish to derive an expression for the normal force Fn exerted on the block by the table as a function of the block's position x. Well, at any given x position, we know that Fty, so the y component of the tension force, is equal to Ft sine theta. And that's just by seeing that the tension force points in this direction with an angle theta. So the component in the vertical direction should be Ft, where the hypotenuse is Ft. The vertical component is Ft sine theta. And since m never leaves contact with the table, we see that the acceleration in the y direction is 0. This implies that the net force in the y direction is equal to 0. So we sum That's what this sigma is. We sum over all of the y components of the forces, and that sum should be equal to 0. Well, here we have three forces acting in the y direction. Firstly, we have Fn, the normal force. Then we have the y component of the tension, so plus Ft sine theta. And these both point up, as we can see in this diagram here. We have the normal force pointing up and the y component of the tension force also pointing up. Then we have gravity pointing down. So we subtract the contribution to the force given by gravity. So we have minus mg. And this sum should be equal to 0. So solving for Fn, we find that Fn is equal to mg minus the tension force times the sine of theta. But we can go one step further. We already found a solution for theta and, more importantly, sine theta, given above. Above, we found that sine theta is equal to h over the square root of x squared plus h squared. So we can just plug that into this expression, giving the following. The normal force is equal to mg minus ft times h divided by the square root of x squared plus h squared. And this is the normal force felt by the mass. As a note, students get 1 point for noting that the net force is 0 and for having the correct sum of all of the forces. So this here is 1 point. Then getting the correct solution, given here in this box, is another point. Students could alternatively plug in for any of the theta functions that they found in part B into the theta here. So alternatively, one could have found that the normal force Fn is equal to mg minus Ft, the tension force, times the sine of, and then you can plug in for any one of these values. We can see what we did below is we plugged in for the first one. So we plug in for arc sine of h over the square root of x squared plus h squared. The signs cancel and it leaves us with the argument here. But we can also plug in for any one of these. So for example, if we used the arctangent, then the solution would simply be mg minus ft times the sine of arctangent of h over x. This is also a perfectly valid solution. The other solution, where we plug in for the arc cosine, is also valid here. Any one of them is valid. I just used the sine one here for ease of notation. Next, let's derive an expression for the magnitude of the net horizontal force F net exerted on the block as a function of the position x. Well, looking at our force diagram, we see that there are two contributions to the net force in the horizontal direction. Firstly, we have a positive contribution from the force of friction. And it's positive because the positive x direction points to the right. So this is the positive x direction. And we have a negative contribution from the x component of the tension force. So we see here that F net is equal to the sum over all of the forces in the horizontal direction. So firstly, we have a positive contribution from the force of friction minus the contribution from the horizontal component of the tension. Plugging in for both of these values, we find that this should be equal to mu sub k for the friction force, this is the coefficient of friction, times the normal force, because we know the force of friction is equal to mu sub k times the normal force. So since we found the normal force above, we'll just plug in for it. We'll plug in mg minus fth over the square root of x squared plus h squared. And then we subtract a horizontal component of the tension. So it's minus ft cosine theta. And it's cosine because it's the horizontal component. Again, I should note that if you found, let's say, this second solution for the normal force instead of this first one, you would just plug in for this one. So although my answer is slightly neater, I could have also used here, this term could have easily been ft times the sine of arctangent of h over x. Both of these are perfectly valid solutions, and they give you the same answer. It's just written in a different way. Next, however, we can plug in for the cosine of theta that we found above. So using this expression here for cosine theta in our expression for the net force in the horizontal direction, we find that the total net force is equal to mu sub k of mg, or times mg minus ft h divided by the square root of x squared plus h squared minus ftx over the square root of x squared plus h squared. So this is the solution to the problem. This is the net force in the horizontal direction. Again, I could have kept the cosine here and instead plugged in for any one of these theta values. Those all would have been perfectly fine solutions. It's just that since I solved for all three, so I solved for sine theta, cosine theta, and tangent theta, my solutions just look a little neater. However, if you just plug in for, let's say, the arctangent one again, it would be a perfectly valid solution. So this is the net force in the horizontal direction. Students get here 1 point for noting that this is the sum of the forces in the x direction, in the horizontal direction. So this, what I underlined in red, is 1 point. Next, the substitution for cosine theta into any one of the possible answers it could be, depending on what you solved for to be theta x, that is also 1 point. So this substitution here is 1 point. And you get 1 point for using the correct f sub n that you found above. So there are a total of 3 points. 1 for the net forces in the horizontal direction, 1 for the correct substitution of theta, and 1 for using Fn, the normal force, which you calculated above. Moving on. Write but do not solve an integral expression that could be used to solve for the work W done by the string on the block as the block moves from x equals L to x equals 0. Well, the work is given by the following equation. The work done on an object is equal here to the integral of the force acting on that object. So here it's Ft dotted into some infinitesimal position. Here, since the block is only moving in the x direction, we have an integral only in the x direction. So the dot product goes away and we're only concerned with the x component. Notice if there was motion in the y direction as well, we would have to consider ft sub y, ft comma y. But because there is no motion in the y direction, we only care about the x component. So the integral here is, well, we have an integral. We want to go from L to 0, as given in the problem here. And we note that there is motion it's moving to the left. So we have a negative sign here. This negative sign is simply because the dx here, this dx, is pointing to the left because that is where the motion is. It's moving to the left. The force points to the left. So because that's the negative x direction, we have a -1 here. And we just plug in for the x component of the tension, which is Ft times x over the square root of x squared plus h squared dx. And this is the integral which in principle one could solve to find the work done by the string on the block. Students get 1 point for using ftx, which is consistent with what you found in C, and students get 1 point for noting that the integral is only with respect to x, and that they have the correct limits, that we go from L to 0, and there's an extra minus sign. And again, this minus sign is simply because given the setup of the problem, you have a block here on a table, and that block is moving to the left. However, we set up our coordinate system as follows. The positive x direction is to the right, and the positive y direction is up. If we reversed this so that the positive x direction were this way, there would be no more minus sign. So this is the solution to D. Finally, does the string do more, less, or the same amount of work on the block as the block moves from x equals L to x equals L over 2 compared to when the block moves from x equals L over 2 to x equals 0? Justify your answer. Well, there are a few ways to go about doing this. Firstly, since you're given a calculator on this exam, you can simply plot the function to get an idea. That's not a proper justification for your answer, but if you're absolutely stuck and you have no clue what to do, you can just plot what the integrand is. The integrand is x over the square root of x squared plus h squared. You multiply it by f of t, but f of t is a constant, so it doesn't matter here. And when you plot this, you get the following. You get a plot which increases linearly for small x. So this is x, and this is x over the square root of x squared plus 4. So here we're using that h is equal to 2. And I use h equals 2 just because that's my choice. I'm putting it into a calculator, so I have to specify what h is. And let's say L is equal to 10. So this is L, which here is equal to 10. And we consider this to be the middle point, which is 5. Then we have here, this is x equals 0. If you plot this function, you find the following. You find a function which goes up linearly and then starts to level off. So what we want to do is we want to compare the work done on the mass by the string. Well, the work, as we know, is the area under this plot because we've put the integrand here. So the question becomes, which area is greater? The area on the left or the area on the right? as you can see, the area on the right is larger. So, intuitively, we can see that more work is done when the block moves from x equals L to x equals L over 2. And that's because there's more area under that function. Physically, however, for from L over 2 is less than x is less than L. So for this portion here, this actually does more work because theta is smaller here. So theta is smaller here, and that implies that more of f of t is in its x component. So ftx, which implies more work is being done. So this is the type of physical reasoning or the justification that would give you a point. You get 1 point for getting the correct answer here, which is that more work is done from x equals L to x equals L over 2. And you get another point for the justification. And again, just to clarify what the justification is, when x is very close to L, theta is smaller. So if we look again at the setup, if the mass is far away, so if this is the mass, we have theta here. Compare that to when the mass moves much closer, let's say to here. In that case, we have another setup which looks like this. Right? So where this is the pulley, then you have the mass here, and this theta is much larger. And as ftx, so the x component of the tension force, is equal to ft cosine theta. Cosine theta has its largest value when theta is small. So, as theta gets larger, the x component decreases. And that means that the integral of that x component, or the work, is smaller if theta is larger. So, to maximize the work, we must minimize theta, which means x is far away, the mass is far away from x equals 0. So, these are the answers to problem 1. Moving on to problem 2, consider the following setup. Cart 1 of mass m1 is held at rest above the bottom of an incline. Cart 2 has mass m2, where m2 is greater than m1, and is at rest at the bottom of the incline. At time t equals 0, cart 1 is released and then travels down the incline and smoothly transitions to the horizontal section. The center of mass of cart 1 moves a vertical distance of h, as shown. At time tc, cart 1 reaches the bottom of the incline and immediately collides with and sticks to cart 2. After the collision, the two-cart system moves with constant speed v. Frictional and rotational effects are negligible. During the collision, is the impulse on cart 1 from cart 2 greater than, less than, or equal to the magnitude of the impulse on cart 2 from cart 1? To answer this question, we consider Newton's third law. Well, Newton's third law says the following. It says something about equal and opposite forces. It says for every action there is an equal and opposite reaction. Or for every force felt by an object, the object acting with that force on the other feels the same but opposite force. So, since we're worried about the magnitude of the impulse, and further, since the impulse J is equal, for a constant force, is equal to F times delta T, and Newton's third law says F, the force felt on cart 2 from cart 1, is equal to negative the force felt on cart 1 by cart 2, we see that J, the impulse when cart 1 collides with cart 2, is equal to the negative of the impulse of cart 2 feeling the effect of cart 1 hitting it. But since we're only worried about the magnitude here, these two things are equivalent. So we find that the two impulses are equal to each other. And that is again because of Newton's third law. So students here get 1 point for saying the correct answer, that the two impulses are equal to each other in magnitude. And students get 1 point for the correct justification. That is, pointing out that the impulse is proportional to the force and that Newton's third law comes in handy here. Next, on the following axes, draw graphs of the magnitude of the momentum of each cart as a function of time t before and after the time of collision, tc. The collision occurs in a negligible amount of time. The grid lines on each graph are drawn to the same scale. Well, to start, we wish to know the acceleration felt by the cart moving down the ramp. This acceleration is equal to the component of gravity moving down the ramp. That is, it's equal to Fg sine theta, which is equal to mg sine theta. However, all three of these components, m, g, and theta, are all independent of time. So this is equal to just some constant. And a constant force gives the cart a linear velocity. So that means it has a linear momentum. So cart 1, which moves down the ramp, has some linear velocity in time up until the time of collision. So I just draw some linear momentum line going to any one of these. And since cart 2 is stationary until the time of collision, it has zero momentum up until tc. So we just draw this flat line. Then we note the following. Since in part A, we found that the change in momentum is the same in magnitude for both carts, we know that however much cart 1 goes down in momentum, it's by that amount that cart 2 should go up in momentum. So let's say we go down by 1 unit of momentum, then cart 2 should go up by 1 unit of momentum. So the solution would look something like this, where afterwards, since it has a constant speed, we have flat lines. However, this is incorrect because we know that m2 is greater than m1. And since p is equal to mv, and after the collision, cart 1 and cart 2 both have velocity v, we see that the momentum after the collision for cart 1 is equal to m1 times v. And the momentum for cart 2 after the collision, p2, so this is p1, and p2 is equal to m2v. So they have the same velocity, but m2 is greater than m1. So the momentum for cart 2 should be greater than the momentum for cart 1 after the collision. Here we see that the momentum after the collision for cart 2 is greater than that for the collision of cart 1, for cart 2. So this is incorrect. Instead, we want to make sure that the momentum after the collision for cart 2 is greater than the momentum after the collision for cart 1. So instead, let cart 1 drop by 2 units of momentum. Then cart 1 moves up by 2 units of momentum and has 1 unit of momentum greater than cart 1 after the collision. So a plot that looks something like this is the correct answer. For point distributions, students get 1 point for having this linear line of momentum for cart 1 and this flat line for cart 2. So collectively, that gives students 1 point. Next, students get 1 point for noting that for times after TC, cart 1 must have a smaller momentum than it did at T is equal to TC, and it must be horizontal. So that would give 1 point. And students get 1 point for cart 1 and cart 2 having the same change in momentum. So here we have a change of 2 units. And here cart 2 also has a change of 2 units. And by units, it's simply how many lines, dashed lines, do you go up. And the final point awarded in this part of the problem is that the momentum at times greater than the collision time for cart 2 is greater than the momentum for cart 1 after the collision. So that is, you get a point for seeing that this horizontal line is higher than this horizontal line. So there are 4 total points awarded in this problem. Next, we wish to show that the velocity v of the two-cart system after the collision is given by the following equation. To do so, we note that momentum here is conserved. So the initial momentum, P0, is equal to the final momentum, PF. So for P0, the velocity at the bottom of the ramp, so the velocity at TC, is the following. Well, using conservation of energy, we say that the energy at the top of the ramp, which is mgh, is converted entirely into kinetic energy at the bottom of the ramp. So at the top of the ramp, we have gravitational potential energy, which is mgh, and at the bottom of the ramp, we have kinetic energy, and that's equal to 1/2 mv, and that's v evaluated at Tc squared. Then, canceling the m's and solving for v, we find that v at the time of collision is equal to the square root of 2gh. So the momentum before the collision is equal to m1 times v at Tc, which is equal to m1 times the square root of 2gh. Next, we know that the final momentum, Pf, is equal to, well, the carts are combined, so the total mass of the two carts combined is m1 plus m2, and the momentum is this mass times some final velocity Vf. We don't know what that final velocity is. Solving for that final velocity, though, which is exactly what we want to solve for, the velocity after the collision, what I call here to be Vf, using the conservation of momentum equation, we equate this equation here to that found above. So we say that m1 plus m2 times Vf is equal to m1 times the square root of 2gh. Then, solving for Vf, we find that Vf is equal to m1 divided by m1 plus m2 times the square root of 2gh. And since we are asked for this exact form, although it may seem simple, we just show that we can rearrange the square root of 2gh into the product of two radicals. That is, we have m1 over m1 plus m2, and we multiply that by the square root of 2g times the square root of h. And we can just move 2g to the left, And we get that this is the square root of 2g times m1 divided by m1 plus m2 times the square root of h. So we have shown exactly what we wanted. As a note, students get 1 point for using the conservation of energy to find the velocity. Alternatively, you could use purely kinematic equations, and that would also give you 1 point. Next, students get 1 point for using the conservation of momentum to find the final velocity. So this equality here gives you 1 point, and this progression here gives you another point. Finally, this progression here, giving you the correct final velocity and plugging in for all of the correct values, gives you your third and final point for this part of the problem. Moving on. Suppose a group of students use the setup to perform an experiment. They measure the mass of cart 1 to be m1 is equal to 0.25 kilograms. The mass of cart 2, however, is unknown. The students perform several trials, and in each trial, cart 1 is released from a different height h, and the final velocity of the two-cart system is measured. The students graph v as a function of the square root of h, as shown below. For part 1, draw a line that represents the best fit to the data points shown. Well, a best fit line should have roughly the same number of points above the line as it does below the line. The line shown here is exactly what that is. So, as we can see, we have 2 data points below the line, so we have 2 below, and we have 2 data points above the line, so 2 above, and this 5th point here is exactly on the line. So that is the answer to the first part of the problem. Students get 1 point for drawing a line with the same number of points above and below the line. So this line here would get full marks. Next, in part 2, use the best fit line to calculate the mass of cart 2. Well, to start, we wish to find the slope of this line. To do so, we need to find at least 2 points that lie exactly on the line. Let's use the following points, which I will circle in orange. We'll use this point here, and also this point. The reason that we use these points is because it's easy to see what values of the square root of h and v that they have. So, for point 1, we have a y value of 0.6 and an x value of approximately 0.35. For point 2, we have a y value of 1.2 and an x value of 0.7. So, the slope here is given as follows. The slope is equal to, well, it's the rise over the run, so it's 1.2 minus 0.6 divided by 0.7 minus 0.35. Then, simplifying this, we get 0.6 divided by 0.35, which is equal to 1.71 square root meters per second. Next, since this line passes through the origin, as we can see here, we can fit it to the following equation. We know it should be y equals mx plus b for a general line in the xy plane. But since it passes through the origin, b is equal to 0. So this line, y equals mx, is exactly the line which matches this. Next, we know that here y is our v value, it's our velocity. And x here is equal to the square root of h. Then, looking at the equation we found above, we see that v is equal to this junk here times the square root of h. So this junk here that I circled in orange is exactly the slope. So we find that the square root of 2g times m1 divided by m1 plus m2 is equal to the slope, which is equal to 1.71. Then, simplifying this and solving for m2, which is exactly what we want to find, we see that m1 times the square root of 2g is equal to 1.71 times the first mass plus 1.71 times the second mass. And this implies that m2 is equal to m1 times the square root of 2g minus 1.71 divided by 1.71. So plugging in for all of these values and noting that the students in this experiment, as described above, found that m1 is equal to 0.25 kilograms, and using that g is equal to 10 meters per second squared, we find that m2 is equal to 0.25 times the square root of 2 times 10 minus 1.71 divided by 1.71. And this is approximately equal to 0.4038 kilograms. And that is the mass of the second cart. As a note, students here get 1 point for the correct slope, so 1.71 approximately. Next, students get 1 point for this equality here, noting that the square root of 2g times m1 over m1 plus m2 is equal to the slope. Finally, students get 1 point for having a mass m2, which is somewhere between 0.3 kilograms and 0.6 kilograms. And since 0.4 is exactly between 0.3 and 0.6, we find that this is a perfectly valid solution. Next, after the experiment, the students use a balance to measure the mass of cart 2 and find it to be less than what was determined in part D. To explain this discrepancy, one of the students proposes that the mass of cart 1 was incorrectly measured at the beginning of the experiment. The students measure the mass of cart 1 again and record a new value, m1 prime. Should the students expect that m1 prime will be greater than 0.25 kilograms, less than 0.25 kilograms, or equal to 0.25 kilograms? Justify your answer. Well, we found above that m2 is equal to m1 times the square root of 2g minus 1.71 divided by 1.71. So, m2 is linearly proportional to m1. So, if m2 prime is less than m2, which is exactly what we find, then m1 prime should be less than m1, which is equal to 0.25 kilograms. So m1 prime should be less than 0.25 kilograms. Students here get 1 point for the correct answer and 1 point for a correct justification. Again, to clarify the explanation, students assume that the mass of cart 1 was incorrectly measured at the beginning of the experiment. And further, they found that the new mass of cart 2 is less than what they determined in part D. That is, m2 prime, the actual mass, was less than what we had measured. So m2 prime is less than m2. Then, to make up for this, we have to ensure that the new m1 is less than the original m1. And again, that's because The two are linearly proportional to each other. And that concludes question 2. Moving on now to question 3. Consider the following setup. A solid, uniform disk is supported by a vertical stand. The disk is able to rotate with negligible friction about an axle that passes through the center of the disk. The mass and radius of the disk are given by m, d, and r, respectively. The rotational inertia of the disk is id is equal to 1/2 md r squared. A string of negligible mass is draped over the disk and attached to the top of the disk at point P. One end of the string is connected to an unstretched ideal spring of spring constant K, which is fixed to the ground as shown in figure 1. A block of mass MB is then attached to the string on the right side of the disk. The block is slowly lowered until the spring disk block system reaches equilibrium, as shown in figure 2. In this equilibrium position, the disk has rotated clockwise through a small angle theta. Give all algebraic answers in terms of MD, R, K, theta, and physical constants as appropriate. To start, derive an expression for the mass MB of the block. Well, to find this, we know that the displacement of the string is the arc length of the displaced wheel. That is, if we look here, we wish to find this length here, because that's the displacement length, and that will give us the amount that the spring has stretched. So these two orange lengths, the stretch of the spring and the displacement of the wheel, are the same. Given theta and given r, it's easy to calculate this orange distance here. It's simply the arc length. So, to start, we say that the displacement of the spring, xd, is equal to the arc length of theta, which is equal to r times theta. Next, the force required to stretch the spring by this amount is equal to negative k times xd. So that's the force required to stretch the spring. So we'll say this is equal to F sub s. And since we're in equilibrium, we know that the net forces should equal 0. We know that the sum over all the forces is equal to 0. So, as the force due to gravity on the block is equal to mbg, that is, the force due to gravity from the block is equal to mb, the mass of the block, times the acceleration due to gravity, g. These forces should sum to 0. So, we say that the net forces, so the sum over all the forces, which is equal to it's equal to the spring force Fs plus the force due to gravity by the block, this is equal to 0. And plugging in for these values, we find that negative k xd plus mbg is equal to 0. But this implies that mbg is equal to k xd. But we already calculated what xd was. So we get k times r theta. And solving for mb, we find that mb is equal to k r theta over g. And this is the mass of the block. As a note for grading, students get 1 point for stating that the sum of the forces is equal to 0. Alternatively, one could have approached this problem from a torque perspective. So, alternatively, instead of pointing out that the forces sum to 0, a student could say that the torques on the disk sum to 0. Either way, that's the first point. The second point is to use the correct forces, or in the case of torques, use the correct torques. Finally, students get 1 point for finding the correct XD value as given here. So those are the 3 points allotted in this part of the problem. Next, consider the following. At time t equals 0, the string on the right side of the disk is cut and the block falls to the ground. On the circle below, which represents the disk, draw and label the forces, not the components, that act on the disk immediately after the string is cut and the block is falling to the ground. Each force should be represented by an arrow that starts on and is directed away from the point of application. To start, this is the wheel. So, at the center of mass of the wheel, which is this dot here, we have the force due to gravity. That always points directly downward. So this is the force due to gravity, Fg. Next, we have the normal force exerted by the axle, or the stand that's holding up the disk. So this is the normal force, Fn. And I'll say this is from the stand, or the axle. Finally, right after the string is cut, this is point P. So the tension force from the spring is still acting on the wheel. And immediately after the string is cut, this force acts tangentially at point P. So for this point here being P, we have the tension force, which points in this direction. And these are all of the forces that act on the wheel. Students get 1 point for having the correct gravity force, pointing downwards. Students get 1 point for having the correct normal force, pointing upwards. And students get 1 point for having Ft anywhere between P, the point P here, and the left edge of the wheel, or of the disk. And that point P is indicated. So alternatively, I could have had f of t here, and that would have been perfectly fine. Or I even could have had f of t pointing right here. All of these are valid solutions, and will give you the point. Next, derive an expression for the angular acceleration of the disk immediately after the string is cut. Well, since f of g and f of n have 0 lever arms, so have a lever arm of 0, the torque that they contribute is 0. So the torque from gravity is equal to the torque from the normal force, and it's equal to 0. That's because these forces act at the point where the axle passes through the wheel. So they have no lever arm, meaning the torque is 0. So the only contribution to tau is from Ft. So tau, the sum of all the torques, is equal to the torque tau sub t, the torque from the tension. And this is equal to the tension force, Ft, times the radius of the wheel, or times the lever arm, which here is the radius of the wheel. So Ft times r. This means that, well, we also know that tau is equal to I alpha, where I is the moment of inertia and alpha is the angular acceleration. But we know that I is given to be 1/2 md r squared. And we multiply that by alpha to give us tau. So we further know that Fs is equal to the spring force, because that's the only force acting on the wheel. So this here should be equal to Fs times r, because after the block is cut, the tension force is equal to F sub s. Again, this is after the block is cut. Finally, what we find after solving for alpha is, well, plugging in for f of s, we find that this is negative k times the displacement xd times r. But if you remember, we already solved for xd. That xd is given to be r times theta. So the total torque is equal to negative k times theta r squared. And so solving for alpha between this equation and this equation, we find that alpha is equal to negative 2k theta divided by md. And this is the angular acceleration on the disk immediately after the string is cut. Students get 1 point for noting that the only contribution to the torque is from Ft, the tension force. This is 1 point here. Just noting that the net torque tau is equal to the contribution from the tension, and that tau is equal to I alpha. So together, those give you 1 point. Next, students get 1 point for equating f of t to f of s, or f sub s. So noting that the tension force is equal to the spring force gives you 1 point. Next, students get 1 point for plugging in for the correct spring force. So negative kxd, that gives you another point. And finally, students get 1 point for using the correct value of xd and the correct value for I. So together, those give you 1 point. Moving on, at time t is equal to t1, the disk has rotated and point P is again directly above the axle. Sketch a graph of the magnitude of the angular velocity omega of the disk as a function of t from t equals 0 to t is equal to t1. Well, to start, what we found is that alpha of t, this is what we found directly above, alpha of t, well, this is equal to the time derivative of omega. Omega is what we want to find as a function of time. But further, alpha of t is equal to the second time derivative of theta with respect to time. So we also know that alpha is equal to negative 2k theta divided by md. So this equation here, boxed in orange, is a second derivative of time of theta, giving you theta times some constant. This is solved by a trig function, a trigonometric function. So we could use sine or cosine. Both of them solve this. And further, let's say the answer is sine. We know it's sine omega t. So here, omega is equal to the square root of 2k over md. And it's the square root because when we take two derivatives, we get omega squared. So the square root goes away, and that gives us the constant in front of theta on the right here. And the negative sign comes from taking two derivatives of cosine. You pick up a negative at least once, the more you take derivatives of cosine. So we also know that at t is equal to 0, omega is equal to 0. And theta has its largest value. So theta is at a maximum at t is equal to 0. The way that this is solved is by noting that theta of t is equal to, it's approximately equal to negative cosine times the square root of 2k over md times time. The reason that we have a negative here is because theta is measured clockwise. And if you remember from trigonometry, theta going counterclockwise is considered positive. So here we have a negative theta because it goes clockwise. So omega, from what we found here, is just the time derivative of this negative cosine. So it's approximately equal to, well, if you take a time derivative of cosine, you get a negative sign times the omega. So we get the square root of 2k over md. The negatives cancel from the time derivative of cosine and the already negative sign that we have here. So we get sine of the square root of 2k over md times time. And just to note, the reason that we've used cosine here is because when t is equal to 0, theta is at its maximum. And the trig function that is associated with its maximum value at t is equal to 0 is cosine. Moreover, we know that omega equals 0 at t is equal to 0. So we know that omega should be something like a sine, because sine of 0, or sine when t is equal to 0, is equal to 0. So we find that plotting this function, omega should be at its largest value when theta is equal to 0. It's just like a pendulum. For a pendulum, we have the maximum velocity when theta is equal to 0. Here, we just have a wheel spinning, but it's the same philosophy as with a pendulum. We have a wheel that's spinning this way, and when this is the equilibrium position, it should be at its maximum angular velocity. So, the maximum for sine should be at t1, and everything else is just the sine function moving up to this maximum value. Then afterwards it moves back down, and it goes negative, and it should continue to go around. So here, 2 points are awarded to students for the problem. 1 point is awarded assuming that the plot shown starts at 0 down here and moves up monotonically until t is equal to t1. Monotonically simply means that the plot is always increasing. So I could have drawn something like that because the plot is always increasing. However, something like this would not have been allowed because at some points it's decreasing while at other points it's increasing. So as long as the plot is monotonically increasing, you get 1 full point. Then students get another point if the plot is concave down. Here, the plot is concave down from t is equal to 0 to t is equal to 1, or t is equal to t1. So that's another full point. So although this plot is also monotonically increasing, it's not concave down. In fact, it's concave up. So this would not be awarded the second point. And as a note, the graders don't care what happened after t is equal to t1. So after this point, I could have followed all the way up, had a nice monotonically increasing function that's concave down, and then gone like this. That would have been totally fine. That would have been awarded full points. Next, moving on to the final part of the problem, let's assume that the disk is adjusted on the support so that the axle does not pass through the center of mass of the disk, as shown in the figure. The block is again hung on the right side of the disk, and the spring disk block system comes to equilibrium, as shown in the figure above. The axle does not exert a torque on the disk. So that's an important point, that the axle does not exert a torque on the disk. For each force on the disk, indicate whether the magnitude of the torque about the axle caused by that force increases, decreases, or stays the same relative to part B. So, let's begin. we have three torques acting on the system. Firstly, we have the torque from gravity. So here we'll call it tau g, and we'll say the torque from gravity, or the torque due to gravity. This torque, well, let's look at the problem. Before, the torque due to gravity was 0. Now, again, the force due to gravity acts at the center of mass, which is the black dot here. However, this torque now has a non-zero lever arm given by this orange line. So the torque has increased from 0. So we say that this torque has increased because the lever arm is non-zero. So that's the first torque acting on the system. The second torque is from the block, so tau b. This is the torque from the block. This torque, well, let's look at the lever arm now. Before the lever arm, well, the force firstly acts this way. That's the force acting tangentially on the wheel. Before, the lever arm was this blue dotted line. Now, the lever arm goes this way, which is clearly longer than the blue dotted line because it's the hypotenuse of this triangle. So, since the lever arm is increased, the torque also increases. So, we say that the torque from the mass of the block has increased because the lever arm increased. So that is the second torque. The final torque on this system is the torque due to the tension of the spring. We'll call this tau sub s. So this is the torque from the spring. And here, well, let's look at the following. Before, the torque given from the spring only had to counteract the torque from the block. Now, because the torque from the block acts clockwise, and the torque from the spring acts counterclockwise, so it just had to be large enough to counteract the block. Now, since the system is in equilibrium, as it states in the problem, we know that the net torque is equal to 0. So, since the torque clockwise is equal to the gravitational force, which acts clockwise because it's acting to the right of the new axle, plus the now larger torque from the block, since this is larger than the original torque clockwise, we see that the spring force has to give a larger torque than it did before. So this has increased to counteract the clockwise, so I'll call that CW, the clockwise torques from tau G and tau B. So we have all three of these torques increased from their values before. And we note we don't have a fourth torque from the axle on the disc because that's what the problem states. So these are the three torques. As a note on grading, each of these torques gives 1 point. So students get 1 point for giving that the gravitational torque has increased because of a non-zero lever arm. Students get 1 point for having stated that the torque from the block has increased, again due to an increase in the lever arm. And students get 1 point for noting that the torque from the spring has increased because the torques are larger now in the clockwise direction. So to ensure that there's no net torque, the torque from the spring has to increase. And referencing that the torque due to the force on the axle changes, or referencing any additional torques, subtracts up to 1 point, or at least 1 point, from the points in this part of the problem. And that's the end of the questions on the AP Physics C Mechanics 2022 released exam FRQ questions. Again, this is for set 1. Thank you.